The formal mathematical definition of the limit of a function will be discussed here, primarily through the so-called epsilon-delta language. Here, we will provide the mathematical definition of a limit. Using the so-called epsilon-delta language, we will formally define that the limit of a function f, as the variable x approaches a real number c, is L. First, we assume that the function f is defined on the union of two open intervals, c, r, and c plus r, as shown on the screen. That is to say, the function f does not need to be defined at x equals c for us to discuss the limit of the function as x approaches c. Simply put, the function f only needs to be defined in the neighborhood of the real number c. In other words, we only need to consider the function values sufficiently close to the real number c. As shown on the screen, when we say the limit of a function f as the variable x approaches a real number c is L, its formal mathematical definition is, given any positive number epsilon, there exists another positive number delta, such that if the absolute value of x minus c is non-zero and less than delta, then the absolute value of the function value f, x minus L, will also be less than epsilon. This kind of abstract definition might be temporarily difficult for beginners to grasp. First, let's think about what it actually means for the limit of a function f to be L. It means that the function value f, x, gets extremely close to the real number L. In other words, the absolute value of f, x, minus L becomes very small. Why do we consider the absolute value here? Because as f, x, approaches the real number L, it can approach from below L, where f, x, is less than L, or from above L, where f, x, is greater than L. Therefore, using the absolute value allows us to simultaneously describe both ways of approaching. As a side note, we frequently see absolute value functions in mathematics because they can easily describe mathematical meaning, just as mentioned above. However, high school math exercises often require students to solve equations involving absolute value functions. This doesn't make much sense because the absolute value function is meant to describe mathematical meaning. We rarely see equations containing absolute value functions in practical applications. Back to the main point, the definition of a limit states that, given any positive number epsilon, if we choose epsilon to be 10 to the power of negative 10, there exists another positive number delta such that if the absolute value of x minus c is non-zero and less than delta, then the absolute value of the function value f, x, minus L will also be less than epsilon, meaning less than 10 to the power of negative 10. This also implies that the function value f, x, is extremely close to the real number L. Usually, the existing positive number delta in this way will also be very small. For instance, delta can equal 10 to the power of negative 8. Therefore, when the absolute value of x minus c is less than delta, meaning less than 10 to the power of negative 8, it means that the variable x is approaching the real number c. By the same token, if we want the function value f, x, to be even closer to the real number L, we can choose epsilon to be 10 to the power of negative 20. At this point, the definition of the limit states that we can still find a positive number delta such that if the absolute value of x minus c is non-zero and less than delta, then the absolute value of f, x, minus L will also be less than epsilon, which is 10 to the power of negative 20. Typically, the existing delta in this way will be even smaller. For example, delta may equal 10 to the power of negative 15. Therefore, for any given positive number epsilon, the corresponding positive number delta that exists will change depending on epsilon. In other words, delta depends on epsilon, or rather, delta is a function of epsilon. So, The correct notation should be expressed as the function delta epsilon, but mathematicians usually do not write it this way because the context implicitly implies that delta is a function of epsilon. Here, we discuss the formal mathematical definition of the left-hand limit. As you can see on the screen, the way it is described is very similar to the usual limit. The only difference is that the absolute value of x minus c is non-zero and less than delta is changed to the variable x is between the real numbers c minus delta and c. Let's recall that the so-called left-hand limit means the variable x approaches the real number c from the left. That is to say, the variable x stays on the left side of the real number c. Simply put, x is always less than c and gradually approaches c. Therefore, when the positive number delta is extremely small, say, if we choose delta to be 10 to the power of negative 15, considering the variable x between c minus delta, and c implies that x is approaching c from the left. Consequently, the entire definition can be understood as, when the variable x approaches c from the left, the function value f, x, gets extremely close to the real number L. In other words, the absolute value of f, x, minus L will be less than an arbitrarily small positive number epsilon. Next, we discuss the formal mathematical definition of the right-hand limit. As you can see on the screen, the way it is described is also very similar to the left zero-hand limit. The only difference is that the variable x is between the real numbers c and c plus delta. By the same token, the so-called right-hand limit means the variable x approaches the real number c from the right. That is to say, the variable x stays on the right side of the real number c. Simply put, x is always greater than c and gradually approaches c. Therefore, when the positive number delta is extremely small, say, if we choose delta to be 10 to the power of negative 15, considering the variable x between c and c plus delta, implies that x is approaching c from the right. Consequently, the entire definition can be understood as, when the variable x approaches c from the right, the function value f, x, gets extremely close to the real number L. In other words, the absolute value of f, x, minus L will be less than an arbitrarily small positive number epsilon. We can clearly see that the definitions of the left-hand and right-hand limits are like removing the absolute value of x minus c and then discussing them separately. In other words, the definitions of the left-hand and right-hand limits are weaker than the original definition of the limit. That is to say, if the limit exists, then both the left-hand and right-hand limits will automatically exist. Conversely, if both the left-hand and right-hand limits exist, the limit does not necessarily exist unless the left-hand limit equals the right-hand limit, just as this theorem describes. We might ask, since the definitions of the left-hand and right-hand limits simply remove the absolute value of x minus c, to discuss them separately, can we also remove the absolute value of the function value f, x, minus L to discuss a weaker definition? The answer is yes, but this is only used when considering the continuity of a function. Later on, we will define the continuity of a function in a way that is extremely similar to the definition of the limit here, so we will also discuss the so-called left continuity and right continuity. When discussing continuity, we replace the real number L with the function value f, c. Therefore, when we remove the absolute value of the function value f, x, minus f, c, we can define the so-called upper semi-continuity and lower semi-continuity. However, upper semi-continuity and lower semi-continuity are usually not discussed in elementary calculus. Yet, they are frequently used in applied mathematics such as optimization problems. Calculate the limit of the function 2x minus 1 as the variable x approaches 2. Intuitively, the calculation is done by directly substituting x equals 2 into the function 2x minus 1, which gives a limit of 3. However, here we are proving it by definition, not by intuitive calculation. According to the definition, given any positive number epsilon, we must find another positive number delta such that if the absolute value of x minus 2 is non-zero and less than delta, then the absolute value of the function value, 2x minus 1, minus 3 will also be less than epsilon. Since the absolute value of the function value, 2x minus 1, minus 3 is less than epsilon, it can be expressed as the absolute value of x minus 2 being less than epsilon over 2. At this point, we can choose delta to be epsilon over 2. Therefore, when the absolute value of x minus 2 is non-zero and less than delta, meaning less than epsilon over 2, we can derive that 2 times the absolute value of x minus 2 is also less than epsilon. Since 2 times the absolute value of x minus 2 being less than epsilon is identical to the absolute value of the function value, 2x minus 1, minus 3 being less than epsilon, the proof is complete. Calculate the limit of the absolute value function of x as the variable x approaches c. Intuitively, the calculation is done by directly substituting x equals c into the absolute value function, which gives a limit of the absolute value of c. Here we are proving it by definition. According to the definition, given any positive number epsilon, we must find another positive number delta such that if the absolute value of x minus c is non-zero and less than delta, then the absolute value of x minus the absolute value of c will also be less than epsilon. Since the absolute value of x minus the absolute value of c is less than or equal to the absolute value of x minus c, we can simply choose delta to be equal to epsilon to obtain the required definition statement, and the proof is complete. Take a look at the description on the screen. It shouldn't be difficult to see how it's proven. The limit representation formulas here are all equivalent. Intuitively, they seem obvious at a glance. However, in mathematics, there is no such thing as mere intuition. Everything must be proven. And the way to prove them is by applying the definition of a limit, which is the so-called epsilon-delta language. You can try to practice proving them as good exercises. This theorem emphasizes that the limit value of a function is unique, which, of course, cannot be understood through mere intuition. It must be proven. The reason we find it intuitive is that we tend to imagine directly substituting x equals c into the function f, which naturally yields a unique value. However, please remember that the limit here is defined using the epsilon-delta language, and there is no concept of intuitively substituting x equals c into the function f. Therefore, from the perspective of the definition, it is theoretically possible that two different real numbers L and M both satisfy the definition of a limit. To resolve this ambiguous question, we must prove that L equals M. Through the triangle inequality, we can prove that L equals M. We will not provide the rigorous proof first. Instead, let's focus on the continuity of concepts. Mathematical thinking implicitly involves philosophical thinking, and it is dangerous to learn mathematics purely through intuition. The development of mathematics relies on starting with intuition and then through rigorous mathematical deduction and proof, confirming that the intuition is correct, which then becomes a so-called theorem that can be used to derive deeper mathematical theorems. Therefore, having a philosophical mindset is genuinely helpful. This theorem describes the limits of functions, allowing us to perform basic arithmetic operations, which, of course, must still be proven. It also tells us why we need to provide an abstract definition to describe limits. It is precisely because we have the epsilon-delta language of limits that we can use it as a tool to prove that limits allow basic arithmetic operations. If we were to rely purely on intuition, how would we even prove it? Therefore, all practical application problems must first be mathematized, translated into mathematical language, before they can be derived using mathematical tools to arrive at a conclusion in mathematical form. This mathematical conclusion is then reinterpreted into the conclusion required by the application problem. This methodology is known as mathematical modeling. While interpreting mathematical conclusions into application-specific terms may vary, the mathematical conclusion itself is eternal and remains an unchanging truth that we can always trust. Equipped with mathematical thinking, including philosophical thinking, we can discern what is truth and what is pseudo-truth. In today's society, people are often blinded by pseudo-truths. With mathematical and philosophical thinking, we can expose these pseudo-truths and return to the essence of the universe. The above theorem does not provide for subtraction, but it can be easily derived using the first and second items of the previous theorem. As shown on the screen, it should not be difficult to understand. The operations here are simply extensions of the previous theorem, whereas we initially considered only two functions. Here we are considering multiple functions. As shown on the screen, both addition and multiplication can be operated by the same token. The same question arises here. Do these need to be proven? They seem intuitive, but they must be proven. How do we prove it? We can prove it using mathematical induction. This is a concept you have already learned in high school. You can try to prove it by yourself, and at the same time, refresh your memory on mathematical induction. This theorem describes the reciprocal and the quotient of limits. We simply need to ensure that the denominator is not equal to 0. As shown on the screen, it should not be difficult to understand. This explains that when the limit of the denominator is 0 and the limit of the numerator is non-zero, the limit of the quotient does not exist. Therefore, this implies a question. What if the limits of both the denominator and the numerator are 0? Does the limit of the quotient exist then? This question is precisely what L'Hospital's rule addresses, which we will discuss in detail later on.